Hey everyone, I am Ms. Hu, your physics teacher. In this video, we will be going through an overview of Unit 3, Waves, which is part of the IGCSE Physics 0625 syllabus for the years 2023 to 2025. Now, this video is an overview, so it's meant to be used as a revision video or a summary for those who have already learned the topics in this unit. It is not meant for you to learn these topics for the first time. So, if you have not learned any of the topics in this chapter yet, and if you're learning this for the first time, or if you prefer to have revision on a specific topic within this unit, please watch my videos on those respective topics instead. This video is meant to be used as preparation for students who are taking their upcoming examinations. This is part of a revision series which I'm making to help students prepare for their IGCSEs. So if you'd like to watch the videos on other units, please check out the videos in the description below or in my playlist. Alright, so let's get started. Now, because this is meant to be a revision video to prepare you for the IGCSE examinations, this video will have a lot of reference to what's in the syllabus guide to make sure we've covered everything we need for the examinations. So you can see, for example, in this video, I have on this side here, these are the statements that I've taken from the syllabus guide. So we'll be going through all of this just to make sure that you do know all this so you can answer your examination questions. Now we start off first with general wave properties. First things first, you must know that waves transfer energy without transferring matter. So when there are waves, for example, whether it's sound waves, light waves, electromagnetic waves, water waves, whatever, all these waves, as the energy travels, the matter does not travel together with the energy. There is movement of matter, but there's no transference of matter, only transference of energy. So I'm going to highlight the word energy here. Next, you must be able to describe what is meant by wave motion as illustrated by vibrations in ropes and springs and by experiments using water waves. So in terms of the wave motion, this is related to number 5 as well as number 6 in terms of transverse and longitudinal waves. So you need to be able to describe what the waves are doing in terms of their vibration, whether parallel to or perpendicular to the direction of wave motion. We'll get to that in number 5 and number 6. Now within those waves, you must also be able to describe the features of a wave in terms of wavefront, wavelength, frequency, crest, or also known as peak, trough, amplitude, and wave speed. Just going to highlight these as well. In this video, I'm not going through the meanings of each of these because by now you should already know what all these terms mean. If you cannot remember, then please watch my video about general wave properties where I explain each of these in detail. Now, you also need to know the equation for wave speed. V equals F lambda, where V is the wave speed, F is frequency, and lambda is wavelength. You also need to know that for a transverse wave, the direction of vibration is at right angles to the direction of propagation. This is the definition for a transverse wave, which you do have to know. So, like I mentioned earlier, this is related to number 2 in terms of the wave motion. The direction of vibration of the wave particles is right angle to the direction of propagation. So sometimes we use ropes and springs to demonstrate these direction of vibrations, and you should also be able to relate this in terms of experiments using water waves. Now you also need to know that transverse waves include electromagnetic waves, water waves, as well as seismic-S waves, which are the secondary waves. On the flip side, you need to know that longitudinal waves have direction of vibration that is parallel to the direction of propagation. So if we were to compare these two, we've got transverse waves, direction of travel or propagation from left to right. You can see in this diagram, the wave particles are vibrating perpendicular to the direction of travel. Perpendicular, so that's a perpendicular sign by the way. As opposed to the longitudinal wave, where the direction of travel is from left to right, and the direction of vibration is also left to right to left to right. So parallel to the direction of travel or direction of propagation. You need to be able to recognize which is transverse and which is longitudinal. And as mentioned here, transverse waves include electromagnetic, water waves, and seismic-S. For longitudinal waves, you need to know that all sound waves are longitudinal, whether they are audible, infrasonic, or ultrasonic. In addition, you also must be aware that seismic-P waves, which are primary, are longitudinal waves. So if you are wondering, do we need to be able to explain what seismic-S and seismic-P are? No. As you can see in the syllabus guide, you only need to be able to identify whether they can be modeled as transverse or longitudinal. Even if you don't know what seismic-S and seismic-P are, well, you should. You can always read up about it. If you'd like to know more, I will be releasing a video about seismic-S versus seismic-P sometime in the future, but it's not a priority right now because, as mentioned, you only need to know whether they can be modeled as transverse or longitudinal. So, for example, if we were to look at a past year question, which is taken from paper 4 variant 2 of the summer 2023 paper, as you can see, the only things they really test you on is just to state whether the P waves and S waves can be modeled as which type. So the answer for P waves, longitudinal, S waves, transverse. Really easy to remember. Remember that transverse waves are the up and down, right? They look like S shape. So S waves, transverse. Therefore, P must be the opposite, which is longitudinal. That's all you need to know. Now, let's move on to wave effects, which include wave reflection, refraction, and diffraction. You need to be able to describe how waves can undergo reflection, refraction, and diffraction. You also need to be able to describe the use of a ripple tank to show reflection, refraction, and diffraction. And for diffraction, you need to be able to describe how wavelength and gap size affects diffraction through a gap as well as at an edge. So to go through this, I'll just go through an overview really quickly. So in terms of wave reflection, so on the slide here, we have a diagram that represents water waves that are undergoing wave reflection. On the left-hand side here, we have the incident waves. Incident waves are the ones that come from the source. So these are the wave fronts. The incident wave is traveling in this direction towards the green color barrier. When the waves hit this barrier, they get reflected back like so. So remember that for reflection, all waves, whether they're sound waves, light waves, electromagnetic waves, water waves, whatever waves, all of them obey the law of reflection, which states that the incident angle is equal to the angle of reflection. Angle that we're referring to in this case is measured from the normal line to the direction arrow. Well, directional arrow. So if I were to just extend the arrow so that it touches the barrier like so. So here's the normal line. Okay, I'm gonna write here normal. And complete the arrow here. This is the angle of incidence, which I'll label as I, and this is the angle of reflection, which I'll label as R. So when we look at water waves, we will not see these directional arrows. We'll only see the wave fronts going right? But if you're wondering, oh, do they actually obey the law of reflection? Yes, they do. Remember, we measure it from the normal line, which I've just fixed the spelling of. Now, what changes and what doesn't change in wave reflection? You do need to keep this in mind. What do not change? Frequency, speed, wavelength, none of these change when the waves undergo reflection. What you should be aware of is that amplitude decreases. What else changes? The direction of the waves. And I'm just going to backtrack a little bit about amplitude. You have to keep in mind that the amplitude decreases because amplitude, if you can recall, represents energy. So when the waves undergo reflection, some of the energy is absorbed or lost during the reflection process, causing the energy to decrease. So that's why the reflected waves have lower energy, and this is shown by its amplitude, so lower amplitude. An excellent example to remember this is sound, because when sound undergoes reflection, the reflected sound you hear, which is the echo, is softer than the original sound. And that's because some of the amplitude has decreased due to the loss of energy. So a lot of students always think, oh, the speed decreases. No, the speed of the wave remains the same. So waves are not the same thing as particles. Like if a particle were to bounce off a barrier, like if you have a ball bouncing off the wall, then yes, some of the energy loss causes the speed to change because the kinetic energy is lost. In the case of waves, we don't have kinetic energy to consider because there's no mass, half mv squared, no mass. So that's why we only observe the energy decrease, showing the amplitude decrease. Next, let's look at wave refraction. So wave refraction is about the change in direction of the wave due to the change in speed. So this is a diagram that shows water waves undergoing refraction. So here you find that the waves have changed direction. Remember that when waves travel from a faster to slower speed, it refracts towards normal, while when traveling from slower to faster, it refracts away from normal. You must remember that in water, the deeper area is faster, while the shallower area is slower. In case you cannot remember which one's faster and which one is slower, here's a little hack for you to remember. You see the word shallower or shallow already has the word slow or slower in there. So shallow, slow. So that's how you can try to recall that, yeah, shallower means slower. In case you're wondering, how does this diagram show that the waves refract towards normal, because faster to slower, right? Just like for reflection, it is based on the comparison of the direction. So if this is the direction, okay, imagine it's straight. I know it's not straight. Here's the normal line, and you can see it has refracted towards normal. The angle is measured from the normal to the direction line. Okay, this is a terrible drawing, so let me just fix that and draw that again. So this here, you see the angle here. Let me color it with a darker color, or rather brighter color. This angle here is smaller than this angle. So it's like the wave has refracted towards normal. Just like for reflection, you also need to know what changes and what does not change. So remember that for all waves, frequency does not change. Now in terms of refraction, because refraction is about a change in speed, therefore speed definitely changes. And because the speed changes, the wavelength also changes, as you can see. So here the wavelength's larger and here the wavelength's smaller. This is very logical because if the waves travel faster, it's like running. Your footprints are further apart. So yeah, the wave fronts are further apart. But if you're walking, your footprints are closer to each other. So just like these wave fronts, they're a lot closer together. This can also be recalled by using the wave speed formula, which is v equals f lambda. Because if the frequency remains the same, a decrease in the speed will cause a decrease in the wavelength. So that's how you can also remember. In addition, you also need to remember that for refraction, you'll find the direction also changes. Now let's go on to wave diffraction. Now wave diffraction is when a wave bends around an obstacle and spreads out. So instead of maintaining that tiny little part of the wave and just only keeping that small part going through, you find that it spreads out. It bends around the obstacle and spreads out. You find the diffraction is more obvious when the gap is smaller. So you can see, for example, in this diagram, smaller gap, larger gap. You can see how, with a smaller gap, the diffraction has caused the shape of the wave to change. From a plane wave, it's become a circular wave. For a larger gap, there's still a bit of spread out, but for the most part, the wave is still plane shape. It's just that they're slightly curved at the edges. With a smaller gap, there's also a wider spread. Now the thing is, how do we determine whether the gap is small or large? Obviously, if you have a side-by-side comparison, then yeah, smaller gap, larger gap. But what makes a gap smaller or what makes a gap larger if you don't have a second gap to compare against? The gap size is compared against the wavelength. So if you compare the gap against the wavelength, so again, let me just highlight here. The gap size here against the wavelength here. See, gap size here against the wavelength here. The gap is considered to be small if it's equal to or less than the wavelength of the wave. Therefore, it should make sense that if you have a larger wavelength, there will be a more obvious diffraction, because when you have a larger wavelength, then the gap size is easier to be smaller than the wavelength, right? So that's why you get a more obvious diffraction when there's a larger wavelength. So this is true not only for gaps, but also for single obstacles. So essentially, a single obstacle also causes diffraction because the wave will bend around the obstacle and spread out. A gap is just quite simply two obstacles placed to form a small opening. And for the obstacle, this is shown on these two diagrams over here. So you can see that if the wavelength is smaller, you kind of get the same thing as this case, where the wave is still plane for the most part. There's just a slight curvature at the edge which goes around the obstacle. With a longer wavelength, obviously the shape can't change to circular because you still get a plane wave on this side, but you can see how the spread is a lot bigger. What do not change? Remember, frequency never changes. For diffraction, speed and wavelength also do not change, because when you think about it, why should an obstacle cause the wave to slow down or speed up? There's no effect on the speed, so the speed and wavelength definitely do not change as well. Does that mean no properties change? Well, not true, but for IGCSE, you only need to know this. So don't stress out about other properties. Just a little add-on. Now, this is not really something that you'll be tested on in IGCSE, but if you're going to take physics at a high level, like A levels, then it might be useful to know this. The most obvious diffraction is when the gap is the same size as the wavelength. So in order to see a more obvious diffraction, meaning that we see a change in the shape of the wavefront from plane to circular, this is most obvious when the gap size is the same size as the wavelength. So in IGCSE, you learn that the most obvious diffraction is just that when there's a smaller gap. But to be very specific, the fact is that it's most obvious when the gap is the same size as the wavelength. So here's a past year question involving wave diffraction. This is taken from paper 4, variant 3 of the winter 2023 paper. And the reason I've just put this in here in this video is because I would like to remind you of a little hint that could help you when it comes to answering diffraction questions in your exam papers. So if you come across a question where there are two different diagrams within the same question about diffraction and both involve some kind of drawing, always remember that you should not be drawing the same thing in both diagrams. If in one diagram you're drawing a circular wave, the other diagram must be plane waves with curved edges, or vice versa. Even if it's not drawing, even if the question gives you a diagram where you see circular waves, if they ask you to draw another wave, you cannot be expecting to draw the same thing as in that original question. It has to be the opposite. So remember that when you're drawing the diffracted waves, make the distinction very clear. Make the difference very obvious. So if one is circular, the other must not be circular. Plane with curved edges. So if you can see in the answer scheme, it is stated as such. Here in 5A, 3 semicircular wave crests. So you should have the circular waves. Whereas in B, 3 wave crests with reduced curvature. So if you're wondering, how do we tell which one is circular and which one's a plane wave? Well, that's why you need to know the factors. So you check, is there a difference in the gap or is there a difference in the wavelength? And in this question, they told us in A, this is red light, while in B, it's blue light, same barrier. So red light has a larger wavelength has a more obvious diffraction. So 5A, that's why you draw the more circular waves. No plane shape, no straight lines. Okay, so semicircular waves, because you don't draw the full circle, right? So semicircular wave. Whereas B, smaller wavelength, so you must draw the waves with reduced curvature. That's how you tell. In case you're wondering, oh, why can't we have both same waves? The exam here is not to test your drawing skills, okay? It's to test whether you can tell the difference. So definitely, the 2 diagrams you draw will be different. Right, let's not dawdle on this. Let's move on to the next. So next we go into light. Starting off first with light reflection. So light reflection is also a wave reflection. Therefore, it also follows the law of reflection. In this case though, you don't have to worry about the wavefronts. You just have the incident ray, reflected ray. And remember that you always measure the angle of incidence and angle of reflection, also known as incident angle and reflected angle. You measure them from the normal line. So if you have a plane mirror, incident ray, measure it to the normal line, that's the incident angle or angle of incidence. Reflected ray, this angle of reflection is equal to the angle of incidence. This angle of reflection is measured also from the normal line to the reflected ray. That covers also number 3. So for number 2 and number 4, in terms of drawing the optical image, now when drawing, always use a ruler. Okay, I know these lines are not exactly straight. Please use a ruler. I'm not drawing with a straight line now because I want to wrap this video up as quickly as possible. Okay, so using your protractor, you should measure out the angle of incidence and reflection for each respective light ray. So because each light ray has a different incident ray and reflected ray, obviously they cannot come up parallel. So using your protractor and your ruler, measure out the angle of incidence, measure out the respective angles of reflection, and you'll find that the light rays would be spread out. To get the position of the image, you need to get the intersection point of the reflected light rays. How do we get that? You need to extend them backwards. So using your ruler, extend them backwards. And if you had drawn them correctly, you will get an image that is at the same line as the object. I'm going to label this O and I. And the distance of the object from the mirror should be equal as the distance of the image from the mirror. Now, in addition to knowing how to draw all this, you must also know the characteristics of the image, which is basically the comparison of the image against the original object. So they have the same size, they're the same distance from the mirror, they're virtual. You should also be aware that they are upright, as well as laterally inverted. Now let's move on to light refraction. For light refraction, you need to be able to use the terms normal, the angle of incidence, and angle of refraction. So again, remember that you measure the angles from the normal line to the light rays. The incident ray is the light ray that comes from the source, and the refracted ray is the light ray in a medium that has changed direction. Now you should also be able to describe an experiment to show refraction of light by transparent blocks of different shapes. For this, please watch my video with the experiment on the different transparent blocks. You also need to be able to describe the passage of light through transparent material, and in IGCSE, it's limited to the boundaries between 2 media only. So for example, air to water or air to glass, you don't have to study 3 or more different media. You also need to be able to define the refractive index as the ratio of the speeds between two different regions. So I'm going to highlight that. So that's refractive index. And you must also know how to use the equation n equals sine I over sine r. The value of n in both of these formula are the same. So one is a ratio of the speeds of the light wave, and the second is a ratio of the sine of the angles of incidence and refraction. Next, let's move on to total internal reflection. Now, you should know total internal reflection by now, but I'm just going to use this slide to very quickly remind you about this phenomenon. So what we're looking at here, this, say for example, is the medium of, say, glass, and light is traveling from glass to air. So what happens when light travels from glass to air? So light travels more slowly in glass and travels faster in air, which means that the light ray will refract away from normal, correct? And of course, you should know by now that every time light refracts, a little bit of the light will be reflected back into the same medium. So this reflected light ray that goes back into the medium, that's internal reflection. So this, I'm just going to underline that. So this internal reflection, that's this line. Well, this light ray that gets reflected back inside. But generally, most of the light ray will be refracted outwards, and because light is traveling from glass to air, light refracts away from normal. When the incident angle increases in glass, the refracted angle in air increases. It'll come to a point where the light ray that's refracted out in air ends up traveling along the boundary. At this point, the refracted angle is 90 degrees. The angle here, which is the incident angle, is now equal to the critical angle, where the critical angle is quite simply the value of the incident angle when the refracted angle, just going to write here as R, is 90 degrees. So that's the meaning of the critical angle. Whoops, my pen is acting up a little bit, so I hope you can read that. So that's the critical angle. So if we look at this equation, so this equation relates the refractive index to the critical angle. And the value of this n is the same as the value of n in the previous slide, which is the ratio of the speeds of wave as well as sine I to sine r. Same value of n. If you've forgotten how this is related, just a quick reminder here that when we use the formula of sine I to sine r, remember that the value of sine I should always be the value of the angle in air, while r is the angle in the medium, as you should have learned by now. So in this case, when we take sine I over sine r, I should be the angle in air, which in this case is 90 degrees, while the value of r is the angle in the medium, which is the one in glass over here, C. If you check sine 90 should give you 1. That's how we get the formula of 1 over sine C. So that's how this formula was derived. Obviously, there's still space for the incident angle here to increase, but there's no more space for the light to refract. So remember that some of the light at this point is still being internally reflected back. But if you keep increasing this angle here, there's no more space for the light to refract back. So what happens is the light will end up completely reflecting back inside. So this is total internal reflection, where the light ray is 100% reflected back inside the same medium. There's no more light refracted out into the second medium. Total internal reflection also obeys the law of reflection, where the angle of incident here is equal to the angle of reflection. But remember that total internal reflection is a subtopic of refraction, not reflection. If this has confused you, well, go watch my video on total internal reflection. I do have a video where I demonstrate total internal reflection with a ray box as well as a semicircular glass block. So if you'd like to see a practical demonstration of this phenomenon, please watch that video. In addition to this, please also remember that when it comes to total internal reflection, it doesn't happen all the time. It depends on whether the conditions are right, and there are two conditions that must be fulfilled for total internal reflection to occur. The conditions are, as you can see, the incident angle must be greater than the critical angle. So here, this is when the incident angle is less than the critical angle. Here, they're equal, and here, this is more than. So I'm going to write here in short form, the incident angle must be greater than the critical angle. Secondly, total internal reflection can only happen when the refracted angle is greater than the incident angle. That means that the light ray must be traveling from slower to faster. Or an easier way to think about it, from a higher optical density to lower optical density. If it were traveling from air to glass, then you'll find that this can't happen because the light ray will always be refracting towards normal. There's no ping jumping back into its own medium like this. So light must travel from higher to lower optical density. I hope you can read my writing. If you can't, well, for those of you with bad handwriting, now you know how your teachers and examiners feel. So please write more neatly than this. Do as I say, don't do as I do. So anyway, let's move on. You also need to be able to describe the use of optical fibers, particularly in telecommunications. And this is quite a popular recurring question. So remember that for optical fibers, this is used in broadband internet or in optical devices like endoscopes, which use light rays to transmit information. So how is it that optical fibers are able to transmit information even though, we bend them? So it's everything to do with how light undergoes total internal reflection. So this is a cross-sectional diagram to show us what's happening inside the optical fiber. So inside the optical fiber, there is an inner core with extremely high optical density. So the optical density of the material inside is greater than on the outside. So you've got a cladding glass and a plastic jacket, of course, to protect the inner core. And when the light ray travels, even though we bend the optical fiber, the light ray will constantly be undergoing total internal reflection because the inner core has such high optical density that it's easy for total internal reflection to occur. So if in case you're wondering how the critical angle relates to total internal reflection, so if we just do a quick understanding of this formula. So if you're critical at math, you should be able to see this straight away. You see, if the material has a high optical density, because this is an inverse, you'll find that the critical angle becomes quite low. So a lower critical angle means that it's easier for total internal reflection to occur. Because if the critical angle was small, let's say for example 20 degrees, any angle above 20, already total internal reflection can occur. If the critical angle was large, like say 60 degrees, that means the angle must be greater than 60 for this to occur. That's why high optical density has a lower critical angle, easier for total internal reflection to occur. That's why the inner core must be made of material with high refractive index or high optical density. And that's why the light ray will undergo total internal reflection very easily. So as I mentioned, this is quite a popular question when it comes to total internal reflection. This is taken from a past year paper, paper 4 variant 3 of the summer 2023 paper, where the students are asked to draw a ray of light undergoing total internal reflection. Always try to draw at least 2 or 3 reflected points. Now, you can draw small little, reflected light rays like this, but if you want to be smart and save time, here's my recommendation. So try to draw them spread out a bit to save your time. So for example, if we draw a light ray like this, you must show that the incident angle and the reflected angles are the same. Use a ruler, of course. As you can see, this question is worth 2 marks. So 1 mark is normally given for showing at least 3 points of reflection. And secondly, showing that the angles are equal on both sides. So as a summary, you must remember that the refractive index can be calculated 3 ways. First is the ratio of the speed of wave. In fact, I teach my students this. The formula is written as the speed of light in vacuum or in air, and you compare this against the speed of light in a medium. Now for IGCSE, we always compare the medium to air. If you go on to A levels, you could be comparing 2 different media, like for example, you're comparing glass against water or diamond against glass, but in IGCSE, it's always compared against air. So that's why for IGCSE and IGCSE level only, the speed of light on the top of the fraction, you can take the 1 as a value of the speed of light in vacuum or air. At IGCSE level, we learned that these values are the same. You can take this as the same value, which is 3 times 10 to the power of 8 meters per second. So that's why this is a formula that I normally would ask my students to remember in terms of calculating this refractive index. So remember that the value of n is the same whichever equation that you use. So if you were to use n equals sine I over sine r, you would get the same value for the same medium. So for example, if you're counting in glass, then this n for glass would also be the same, and likewise for the 1 over sine c formula. So remember that when using the sine I over sine r formula, because we are comparing the medium against air, you always put the angle in air at the top and the angle in the medium at the bottom. So just a quick reminder about this, because sometimes the question may give you a situation where the light is traveling from the medium to air instead. So for example, from water to air. So even though this angle should be the incident angle and this angle is the refracted angle, when putting it into the formula, it is wrong to put the angle like this. So this is wrong. So don't get tricked. Even though the question gives you from water to air, the angle in air goes on top, even though it's a refracted angle. Remember that you have to make the modifications for calculations. So this angle goes on top while this angle goes at the bottom. This formula is simplified from Snell's law, and in this case, it is based on the assumption that the light is traveling from air into the medium. So from air to water, air to glass, air to oil, air to plastic, air to diamond. At IGCSE level, from air to medium. So that's why if they give it to you in the opposite direction, you must remember to put the air on top and the medium at the bottom. Okay, enough of this, let's move on. For lenses, now, you need to be able to describe the action of thin converging and thin diverging lenses on a parallel beam of light. So remember that for converging lenses, the light rays will focus, and for diverging lenses, they diverge. You must also know the terms focal length, principal axis, and principal focus, also known as a focal point. You must be able to draw and use ray diagrams for the formation of a real image by a converging lens. If you're doing extended, then virtual image by the same lenses. You must be able to describe the characteristics of the image using enlarged, same size diminished, upright inverted, and real virtual. You have to be able to describe the use of a single lens as a magnifying glass. you have to know how the virtual image is formed. That means the diverging rays are extrapolated backwards and they don't form a visible projection on a screen. And how the converging and diverging lenses are used to correct long-sightedness as well as short-sightedness. What a mouthful. So of course, to answer all this, it helps if you know how to draw. So we'll get to the drawing in a moment, but just to remind you, in terms of real and virtual, remember that real images can be projected on a screen. In fact, this is the definition. So if you were asked, why is an image a real image? The answer is, it can be projected on a screen. So that's what you write. Whereas for virtual images, it's just the opposite. They cannot be projected on a screen. So these are the answers that you can write if you were asked to explain or describe real and virtual images. Now let's go into the drawing. Right, so in this video, I'm not going to be drawing the ray diagram for all the different positions of the object compared to the convex lens, which you should know how to do by now. I'm just going to draw two diagrams as a reminder on how to complete the ray diagrams. Now remember that you need to draw at least two light rays that come from the same point on the object. One light ray should come out parallel to the principal axis. I'm just going to modify this a little bit. So we've got one light ray parallel to principal axis. Any light ray that comes out parallel to principal axis when going through the lens, it will come out through the focal point. Okay, so that's not where it starts off at. Now this particular software, it's not an actual whiteboard, so it's difficult for me to draw and show you the start and end point. I have to create the elements and then move them, and it likes to snap to some weird endpoint which I don't want it to snap to. So that's why I'm creating and shifting these lines to the correct position. So bear with me. So we've got one light ray parallel to principal axis and goes through the principal focus. The second light ray, which as teachers we always recommend to students to draw, should be the one that goes through the optical center of the lens. So this one starts here and this one goes through the optical center. And as you can see, if you drew it correctly with your pencil, you should already get an intersection point. So that's where the image is formed. Now, the image characteristics is always compared against the object. So you should look at the image and look, is it the same size? Is it larger than or smaller than the object? Is it inverted or upright? Is it real or virtual? So in terms of size, it's very easy. You actually measure using your ruler the height of the image and compare that against the height of the object. If drawn to scale, the comparison of the size is exactly that. In terms of whether the image is inverted or upright, you can see that the intersection point is below the principal axis, which is why the arrow points downwards, compared to the original object where the two lines start above the principal axis. So therefore, this is an inverted image. And because it's formed on the opposite side of the lens, you can imagine that you've put a screen here. The image is being projected on the screen. That's why it's a real image. When drawing the light rays, always draw arrows before and after the lens. So one arrow before, one arrow after, one arrow before, one arrow after. In fact, it's better to put the arrow in the middle here to show clearly that these are light rays and not just random lines that are being drawn. Is there a third light ray you can draw? Yes, you can draw a light ray that goes through F and comes out parallel to principal axis, but usually that's not the recommended light rays to draw because it actually can be more confusing in certain situations. So that's why the teachers always advise to draw these two light rays. So I'm just going to write that over here in terms of your guidelines. Regardless of wherever the object is placed, whenever you want to draw the ray diagram for the convex lens, remember to draw these light rays. So number one, you draw the light ray that is parallel to the principal axis, and after it goes to the center of the lens, it should go through the principal focus on the other side, F. The second light ray that you want to draw should be It's just straight through the optical center. And the intersection you get, that's the position where the image is formed. Taking these same two guidelines, you can also draw the light ray for an object that's placed really close to the lens like this. So again, I'm just going to show the formation of the image. Okay, like this. I'm going to shift it. There you go. Okay, so one light ray parallel to the principal axis. And then this light ray will go through the principal focus of F1. It's snapping again in weird positions. And then the second light ray just goes through the optical center. Now, because the object is placed so close to the lens, its distance from the lens is less than the focal length of the lens, you'll find that the light rays that have gone through the lens are diverging on this side. So, however you try to extend these light rays, they will not be intersecting on this side of the lens. So, how do we get the image then? This doesn't mean, oh, no image. No, there is an image formed. You need to extend them backwards. So we're going to extend them backwards. In this case, I'm just going to draw. So remember to use your ruler when you extend them backwards. And you'll find that because the image is formed behind the lens, it can't be projected on a screen. So that's why we end up getting a virtual image. And as you can see, this image is now enlarged, upright, and virtual. And that's how we draw the image in this case. And this is the exact situation in how a single convex lens can be used as a magnifying glass. So if you recall, when you use a magnifying glass, you have to put the magnifying glass really close to the object, and that's how you can get a really large virtual image. Let's move on. Now, for concave lenses. Good news! You don't have to draw the image for concave lenses. Yay! Taken out of syllabus already. So let's move on. So one more thing you need to know about lenses is how lenses are used to correct vision. As stated here in the syllabus, you need to be able to describe the use of converging and diverging lenses to correct long-sightedness and short-sightedness. Now, if we take a look at this diagram, this shows us the correct focus of the light rays entering the eye. So here, this is a cross-section of the eye. This is the lens of the eye, and at the back here is the retina. So how we're able to see clearly is the light rays that enter our eyes will refract through the lens of our eye and focus at the retina, which is at the back of the eyeball. So the retina is where all the optic nerves are, which are able to pick up the light rays and then informs the brain on what we're seeing. And of course, if the light rays are focused properly, then we get a sharp, clear image. People who are long-sighted can see far away things more clearly, long, whereas the things that are near them are blur. Now, so what happens in long-sightedness is that the light rays that enter the eye end up focusing behind the retina instead of on the retina. So the retina does not pick up a sharp, clear image. Because the light rays have traveled too far away, in order to correct long-sightedness, we need to use converging lenses, also known as convex lenses. So the convex lens will help to focus the light rays so that they come closer towards the retina. So you can see here the convex lens focus the light rays a little bit, and then as the light rays enter the lens of the eyeball, they get refocused so that they will converge on the retina, producing a sharp, clear image. Now, people who are short-sighted can see closer things clearly, but things that are far away appear blurred to them. So when they look at faraway objects, what happens is that the light rays end up focusing in front of the retina. So that's why they also don't get a sharp, clear image. So to correct short-sightedness, we will use a diverging lens, also known as a concave lens. Because the light rays end up focusing in front of the retina, we need to extend the focus a little bit to the back. So by using a diverging lens, the light rays will be diverged before they are focused as they enter the lens of the eyeball. And then when the light rays meet at the retina, then the wearer of this lens will get a sharp, clear image formed. So when it comes to correcting vision, you must know which lens is used for which kind of vision issue. That means for long-sightedness, you need to know that a converging lens is used, i.e. convex lens, and for short-sightedness, diverging lens is used, or also known as a concave lens. You may also be required to be able to draw the light rays that pass through the lens and then into the eyeball. So remember that the light rays must always focus at the back on the retina. The next thing you need to know is about light dispersion. So you need to describe the dispersion of light as illustrated by the refraction of white light by a glass prism. So dispersion is quite simply how white light, when it refracts in a glass prism, it ends up separating into the different colors of the rainbow. You must know the traditional 7 colors of the visible spectrum in order of frequency and in order of wavelength. So the reason why light disperses is because due to the different frequencies of the colors, they will refract at different angles, causing them to spread out. And that's why you can see the different colors within the spectrum. You must know the order, which you should have learned since you're in primary school. If you start off with red, the next color would be orange, yellow, then green, blue, indigo, and violet. So for me, I remember this as the Roy G. Biv. Some of you have your own methods of remembering the colors. Please use whatever method that works for you. You must also remember which one has the longest wavelength. So red has the longest wavelength and violet has the shortest. So when moving across the spectrum, the wavelength decreases and the frequency increases. So violet has the greatest frequency while red has the lowest frequency. You're expected to know this. Now, if you have a light source with only one color, that's monochromatic. The correct definition for that is that the light has a single frequency. So remember that different shades of color have their own frequencies as well. So if the light source only emits that single frequency, that's a monochromatic light source. The kind of question that could come out, and it has come out in the past before, they may ask students to draw the light rays that go through the prism and then out into air. Normally you only ask to draw 1 or 2 light rays as a comparison. So remember that red is on top, while violet is at the bottom. This is, of course, further exaggerated when it goes out into air. You may not be necessarily asked to compare only red and violet. Sometimes you could be asked to compare the colors in between, like maybe yellow against blue. So as long as you know this order, then you should know that, for example, yellow is on top, while blue is at the bottom compared to that yellow color. So you have to know how to draw this in 2D. Of course, use pencil to draw this. Don't use color pencil in your IGCSE exams. I'm just putting color here as a visual reminder. Next, let's go on to electromagnetic waves. Wow, there's a lot of things to know. So you must know the electromagnetic waves in terms of what the waves are within the spectrum, in terms of their frequency and order of wavelength. So you can see number 3, you've got to know all these different electromagnetic waves as well as their uses, the harmful effects of some of these waves, and you must know some properties here, which are, for one, all electromagnetic waves travel at the same high speed in vacuum, and that value is 3 × 10⁸ meters per second, and this is approximately the same in air. Now, in addition to all this, you also need to know the communication with artificial satellites is mainly by microwaves, and that some satellite phones use low orbital artificial satellites, and some phones as well as direct broadcast satellite television use geostationary satellites, and that many important systems rely on electromagnetic radiation, including mobile phones, Bluetooth, and optical fibers. Now, to remember all this, it just helps to know basically the electromagnetic spectrum. So to summarize all of that in the past 2 slides, I'm just going to show you this and remind you that you need to know the electromagnetic spectrum as well as your order. So if we start with the wave with the longest wavelength, that's the radio wave. As we go across the electromagnetic spectrum, the wavelength decreases, while as you can see, the frequency increases. So starting with radio waves are used to broadcast radio and television. Then we move on to microwaves. Microwaves are just quite simply high frequency radio waves. They're used in cooking, like in microwave ovens, as well as radar, telephone, satellite communication, and other signals. Next, infrared radiation. Infrared is always emitted when there's any heat. So this transmits heat from the sun, fires, as well as radiators. In the electromagnetic spectrum, the only visible part is visible light, which is basically the light spectrum. It enables us to see things. Then we go on to ultraviolet, which is absorbed by the skin and used in fluorescent tubes. As we go on to the higher frequency waves, these include X-rays followed by gamma rays. So X-rays are used to view inside of bodies and objects in medical imaging, like in X-rays and MRIs. Whereas for gamma rays, they're used in medicine for killing cancer cells. Now, in addition to the uses, you must also be aware of the dangers of electromagnetic radiation, specifically these 4 dangers. For microwaves, the danger includes internal heating of body cells. Infrared would cause skin burns. Ultraviolet could cause damage leading to skin cancer and eye conditions, whereas X-rays and gamma rays can cause mutation or damage to body cells. You also need to know about analog and digital signals. You must know the difference between these two, and that sound can be transmitted as digital or analog. So analog basically are continuous signals, whereas digital are more on-off signals. So the benefits of digital signaling compared to analog is that there's an increased rate of transmission of data and increased range due to the accurate signal regeneration. So in this case, this means that if, let's say, we need to increase the amplitude of the waves, the problem with analog signals is that if you were to increase the amplitude, if any noise or interference was picked up, that noise and interference would also be amplified. In the case of digital, if it picks up any noise or interference, it's easier to filter out because the digital is just up, down, up, down. So any additional noise can be filtered out because it's just a recognition of the highs and lows. Whereas for analog, any noise is difficult to filter out because it has also become part of the analog signals. So if you don't know what all this is, please watch my video where I explain clearly the difference between analog and digital signals. And now we come to the final part of this chapter, which is on sound waves. So these are some of the many things you need to know about sound waves. So instead of reading out all of this, let me just show you the summary in my following slides, which is that sound is a longitudinal wave. It needs a medium to travel. You must know about the ranges of sound waves where the audible signal is between 20 to 20,000 Hertz. If the frequency of the sound wave is less than 20 Hertz, that's known as infrasonic, while if it's greater than 20,000 Hertz, it's known as ultrasonic. You must know that sound travels the fastest in solids, followed by liquids, then gases. The approximate value of speed of sound you must know in particular is the speed of sound in air, which is between 330 to 350 meters per second. In terms of liquids and solids, they don't necessarily test you on this, but it is helpful to know as well. The speed of sound in liquids is generally between 1,000 to 1,500 meters per second, whereas in solid it varies, but it's normally at least a few thousand meters per second. You should also know that frequency affects pitch. The lower the frequency, the lower the pitch. The higher the frequency, the higher the pitch. Amplitude affects loudness. So a low amplitude is softer, whereas a higher amplitude is louder. You should also know the applications of ultrasound, and in your syllabus, you just need to be aware that they are used for non-destructive testing of materials. That means they use sound waves to try to detect any flaws within the materials. And the same technology is also used for medical scanning of soft tissue, which we normally know as ultrasound. So this is normally used to get an image of a fetus within a mother's womb. And besides this, it can also be used for other kinds of medical scanning. For example, if you're looking for any anomalies or cysts within the soft tissue. Exactly the same technology is also used for sonar, which is normally used to determine the depth of the ocean or to look for things in the sea. For example, if they're looking for a fish or things under the water, for example, the shipwreck or other objects under the water. You have to also know the experiment to determine the speed of sound in air, and this is actually quite logical. To determine the speed of sound, it's just a matter of understanding how to calculate speed, which is of course using the formula of speed equals distance over time. So the experiment would involve using a timer. So the timer is started and stopped by using sound sensors. So we'll have to place the sensors at a fixed distance from each other. So for example, if you're putting them at 1 meter apart, that will be the value of the distance substituted in the formula. So when we make a sound, the sound would then travel in this direction from the starting sensor to the stopping sensor. So the timer will start when the sensor first picks up the sound on this side, and it's stopped when this sensor picks up the sound. So that's the time that you put into the equation, and that's how you then would calculate the speed of sound in air. Other calculations that you need to know how to do could involve determining the depth of the ocean under the ship, or to determine the time difference between the echoes that we hear in this case. So for example, if a sound is made, they will hear two sounds. So first is the sound traveling from the source to the ears directly, and the second sound is because the sound has traveled and echoed off the wall, and you may be asked to calculate the time difference between that first sound and that echo. So if you find that the sound has bounced back, then you need to make a modification of the speed formula. So if speed is basically distance over time, in this case, the distance in both of these situations have traveled back and forth. That means if this was d, let me put a different color. If this was d, distance would basically be 2d over time. So that's why sometimes you'll see this written as v equals 2d over t, and depending on the question, you just need to rearrange the variables to calculate what needs to be solved. For example, if you're counting time, or if you're counting distance, or if you're counting speed. And that is it for this overview video. So I hope you found this video to be educational and helpful. If you did, please click like, and of course subscribe for more physics lessons from your physics teacher, Miss Ho. If you did find this video helpful, please help me keep making free educational video lessons and lab practicals. Donations are welcomed at my Ko-fi page, which is ko-fi.com/physicsrocks. For more notes, quizzes, and syllabus updates, please visit my website at physicsrocks.com. All the best for your upcoming examinations and happy studying!